We're going to be talking about 14.7. 14.7 is looking at optimization of multivariable functions. So we want to be able to find maximum values and we want to be able to find minimum values. And this type of work has applications to all sorts of sciences and social sciences. The learning goals for today: 1, we want to be able to find the local max and min of two variable functions just by evaluating it graphically. So taking a look at what the graph looks like. We also want to be able to define and find critical points, and we need to be able to use the second derivative test to evaluate whether a critical point is a maximum, a minimum, or a saddle. And then finally, we're going to use, we want to be able to find the global max and min values, so the ultimate maximum and the minimum values on closed bounded domains. It's actually a lot of material, but I think it's really interesting material, and it builds really intuitively on some of the things that you've done previously in calculus. So let's look back on what we've learned about finding maximum values and minimum values from our previous calculus work. Let's say we have a single valued function, f of x, and just graphically evaluating how do I know whether or not a point is a maximum or a min value? Well, I can look at this graph and I can say, oh, about at this point A, it looks like f of A is one of the higher points on the graph. Notice that I'm going to call A a local maximum, and local is saying that it's the highest point in its little neighborhood. If I look at the points nearby A, it's the highest one of those. But if I look way over here on this edge of the graph, we see that there might be some points higher than A that are over there. We don't care about those. We only care about the things that are local to A, or close by A. So this point is a local max. We have this point C down here that I would say is a local min. And again, we have some minimum values that might be lower than it if I continued my F graph way down here. But it's the lowest point that we have in its neighborhood. Now, how do we know that something's a local max or a local min? Algebraically, we defined a critical point for a two-dimensional function is going to be one in which the derivative at that point is equal to 0. Or we have a horizontal tangent line. So that's one way to be able to tell that at this point A we have a local max. So we see that f prime of A is equal to 0. That's enough to tell me that I have a critical point. But how do I know that it's a max? Recall that we have a second derivative test for single variable functions. And we found that if the second derivative at that point A is negative, then we know that A is going to be a max. What does it mean for the second derivative to be negative? The way that I think about it is that my function is being pulled downwards, so that as I travel along this path, the acceleration or the second derivative is pulling it this way, and that's why it's the highest. For our min values are critical points where my second derivative here at C is greater than 0, meaning my acceleration is pulling me upwards. But let's take another look at point B. Point B is a place, hopefully, I sort of tried to draw on the graph. So point B is a place where my derivative equals 0. So I'll write that down. At B, f prime of B is equal to 0. But we see that B isn't a local max or a local min. That we just characterize it as a critical point that's sort of a dud. It's not a max or a min. And that's possible for multivariable functions as well. So, let's take a look at what it would mean for a multivariable function to have a max or a min. So let's say we have some multivariable function. This is going to be my sort of go-to generic graph of a multivariable function. And just from visual analysis, I want to know what is the maximum value on this graph Well, it's going to be sort of the highest point that you get to on this graph, right? It's going to maximize the z values. A way to talk about that more rigorously is that the tangent plane at my point should be an exact horizontal tangent plane, that I could place this down right on top, and the tangent plane right at that red point, I'll label that red point the point AB. So the functional value is f of AB up here. That this tangent plane is exactly flat. And how can we characterize that algebraically? Similar to what we saw before, we know that we have a critical point. Well, maybe I'll say we know that in order to be a maximum value for our function f of xy, we would have to have the fact that my partial derivative with respect to x at AB has to be equal to 0, and my partial derivative with respect to y at AB has to be equal to 0. Notice this is exactly analogous to what we've seen before. That really all that this is saying is that if I take a tangent line in the x direction, I would want that to be exactly flat, and if I take a tangent line in the y direction, I would want that to be exactly flat as well.